in 10.3 last time?
Yeah.
And I said, they'll do it on your own. I'm sure you all did it over spring break when you weren't having fun.
Uh-huh.
So we're gonna do it again together to make sure you guys all did it right. That's what we're gonna do. Just to finish that one up. So 10.3, remember, was how to do calculus with how to find equations of tangent lines and so forth with polar coordinates, so the introduction to polar coordinates. And the reason I'm wearing the cool shirt today is because we're doing areas in polar coordinates in 10.4, which some would argue is the hardest section of all of Math 60. Some would argue that, hence the shirt. But we'll do that after we finish 10.3. Something's a little bit different. The exam on chapter 9 and 10 isn't for 2 weeks. And today's the last day of chapter 10. And the reason we're not doing it for 2 weeks is I want to make sure you have enough time to do the work, get stuff turned in, get my feedback before the exam. So if you look at the schedule, when I see you on Thursday, we're actually starting chapter 11. When I see you next Tuesday, we're going to do more of chapter 11, and then we'll stop and review for the test and take the test. Chapter 11 is really long. That's all we're doing from after this test. That's all we're doing until the end of the semester. There'll be one more exam on chapter 11, and then the final. Questions, comments? Yes, sir?
Isn't that when we have the midterm and then we have a week for like studying and then it's the final?
Exactly. Let's look at the schedule. So the chapter 11 exam is on Thursday the 16th, and exactly a week later is the final exam. So basically you get that exam back, you review a little bit, and then you take the final.
That's fine.
But the good news is, chapter 11 will all be fresh because you'll have just taken that exam, right? So you only have to review the other things. That's the theory behind it. Okay, so let's pick up where we left off. Page 101, and I notes 10.3. We were talking about tangent lines in polar coordinates. And I think, if I remember right, just before we were done, I showed you this formula for how to find the slope of the tangent line in polar coordinates. You guys have that in your notes, hopefully? And I told you you don't have to memorize it, you don't have to derive it, you can if you want to, but I will give you this on an exam, you don't have to memorize it. But this is how you find the slope of the tangent line if everything's in terms of r and theta. Because the slope of the tangent line is it has to be a change in y over a change in x. This is the formula that we use. So given that, the question for example 5 is to find the equation of the tangent line for this polar equation at this theta. Is that correct? Do I have it? Yes. That's what it's asking. Everyone clear on the question? I didn't write the whole question up here. Find the equation of tangent line. What do we need for an equation of the tangent line? Or any line? Oh, I heard that. Slope. And a point. So we need a slope and a point. Which one do you want to find first?
Slope.
Okay, let's find the slope first. You want us to find the slope first? How are we going to find the slope of a tangent line? I can't hear you.
Don't you find the derivative of the equation given?
That's a good question. Derivative of what equation? This equation? With respect to theta? Because you know the equation of a line is y minus y1 equals m times x minus x1, right? That's the equation of a line. This m, it has nothing to do with r's and thetas, right? So this m is a change in y over a change in x. So we actually have to do this to find the slope of the tangent line. We have to do this mess up here to find that. And this mess has all kinds of stuff going on in it. It has dr d theta, which is, I think, the derivative you were talking about, Joseph, I think. That's the derivative of our r function with respect to theta. It also has some other trig in it, and just r by itself, and so forth. So to find the slope of the tangent line, I first need to find dr d theta. Dr d theta. That's just the derivative of this function with respect to theta. Which in this case, the derivative of this function is 8 times derivative of sine is cosine theta. That's the derivative here, because the derivative of this term is 0 plus 8 times the derivative of sine. So then to find the slope of the tangent line, I have to take this and plug it in there, everywhere I see a dr d theta. So let's see if we can get that. dy dx equals, instead of dr d theta, I'm going to put in 8 cosine theta. I'm going to get another color so I can mix and match for you. This dr d theta right here is dr d theta right there. So all I've done is dr d theta times sine, dr d theta times sine, plus r. Here's r. What's r? Yeah, this whole mess is r over here, right? So I'm going to put r in there. I'll put it in a box just so you can see it. 3 plus 8 sine theta. That r is going to get multiplied by cosine theta. So there's my r. That's just the numerator of that formula. Just plugging things in. Over 8 cosine theta again, times cosine theta, minus r times sine theta. So this is r again right here, here, and this was the dr theta here. That's a nice mess. Questions on where all that came from? What am I trying to find again?
Slope.
The slope. So the slope is a number, right? Yeah, so thank you, Chad. So I want to find the slope at this theta value. So I actually need to plug my pi over 6 into everything there to find out what the slope is at that theta. So all those thetas are now going to become pi over 6s. See if I can squeeze it in here. 8 cosine of pi over 6 times sine of pi over 6. I don't think I'm going to fit it. Hang on, going down the next line. I'm not going to fit. 8 cosine of pi over 6 times sine of pi over 6 plus 3 plus 8 sine of pi over 6 and cosine of pi over 6. This is fun. Right about now, you guys are going, oh, she wasn't kidding when she said we need to know our trig. So I'm replacing all my thetas with pi over 6s. What is pi over 6?
30 degrees.
It's a 30-degree angle. So for those of you that hopefully remember a little bit of trig, when you have a 30, 60, 90, 30 degrees is actually pi over 6 radians. What's the relationship between those three sides? 1, 2, square root of 3?
Yeah.
That's one of the things that if you have it memorized, your trig life is a lot easier. Bless you. Okay, so looking at that should help me figure all this out. Let me go over this next line from the next board. So I have 8 times the cosine of pi over 6, which is
Root 3 over 2.
root 3 over 2, times the sine of pi over 6,
1/2.
which is 1/2, plus 3 plus 8 times our 1/2 again. So basically what's happening right now is every cosine is going to get replaced with a square root of 3 over 2. Sorry, every cosine is going to get replaced with a square root of 3 over 2, and every sine is going to get replaced with a 1/2. We're just replacing all those in here. Okay, so I lost my place. 8 plus 3 plus 8 sine times a cosine. This down here is the same. 3 times cosine times another cosine. 3 plus 8 times 1/2 times the sine, which is another 1/2. I think I just replaced all the cosine pi over 6s with root 3 over 2, and all of the sines with 1/2. Good? Messy, but we'll clean it up. Gotta know your trick. So things are actually gonna clean up nicely. Because here, when I multiply this 8 times these two fractions here, you see those denominators are gonna reduce? So that's a 4 down here, reduces with that 8, so I'm just left with 2 root 3. 2 root 3. Right here I have 3 plus 4, 8 times 1/2 is 4, right? Which will be a 7 in a minute. Just clean it up a little bit. Is okay? What happens here?
You get 2 root 3.
You get 2 times root 3 times another root 3. So that's just 2 times 3? What'd you say?
I thought the root 3 over 2 and root 3 over 2 would just be 3 over 4.
It is.
Oh.
Yeah, so this is 3 over 4, but when you multiply it by 8, the 4 and the 8 will reduce. So it's just 6.
Oh, yeah.
So I think we're all in the same place. You got 12 over 2 is 6. That's just 6 minus, this will be the same 3 plus 4 in here, times 1/2. We're almost there. Clean it up a little bit. Wasn't very nice of me to have you do this on your own. Now that I see how messy it is. So this is 7 root 3 over 2. 7 root 3 over 2 for this part. 6 minus 7 over 2. I couldn't hear you say.
So don't the denominators have to be?
Yeah, the denominators, we have what this is called a complex fraction, where you have fractions inside of fractions. There's a couple different ways to clean it up. The easiest and simplest way is just to multiply the top and bottom by a common denominator, which in this case is just 2. That'll get rid of these fractions. So I'm going to multiply everything here by 2 and everything here by 2. Distributing that through will get rid of the messy fractions. So I have 4 root 3 plus 7 root 3. Okay, so this 2 got multiplied here, that 2 reduced over 12 minus 7. Which is just, finally, 11 root 3 over 5. What is that again? That's my slope. Okay, so there's my slope at pi over 6. So we had said, to find the equation of the tangent line, we need a slope. We got it, finally. And we need a point. A point is x, y. We don't have that yet. Luckily, it's easier to get than the slope. How are we going to get the x, y?
X equals r cosine theta.
The definitions that we started with weeks ago now, because we went on spring break. The definitions for polar coordinates for the x and the y. So on the very first page of our notes on polar coordinates, that's how you find any x and any y. So in this particular case, let me bring that over here so I can mix it up. X equals 3 plus 8 times 1/2. Right, because again, it's still at pi over 6. So the cosine of pi over 6 is, the sine of pi over 6 is still 1/2. That's the same thing we have in here, right? That's the r. You guys okay with that part? That's the r times cosine of pi over 6. And y equals r times sine of pi over 6. So I'm plugging in my pi over 6 into those formulas as well. I'm sure you guys all wish you had your own shirts right now that said something else. I don't know what it says, but I don't think it says this. I think we can't repeat some of it. So this was just the 7. Cosine of pi over 6 was root 3 over 2. So that's 7 root 3 over 2 is the x. And y is 7 times 1/2, so it's 7 over 2. What is this? Besides exhausting and hard and messy. Yeah, your Cartesian coordinates, your x, y's. We know that x is 7 root 3 over 2, and y is 7 over 2. This is our point. This is the point that when you're on this polar equation over here, when you get to theta equals pi over 6, that's the x and y that you are if you're going to measure over x and y and find it when you're graphing it. So finally, we have a slope. It's over there, our m. We have a point. So now we're ready to write the equation of the line. Y minus 7 over 2. What was my slope? I lost it. 11 root 3 over 5. 11 root 3 over 5 times x minus 7 root 3 over 2? I can't see it. Yeah? So this is the equation of your tangent line. If you really wanted to, you could distribute and add like terms and whatever. I'm not too worried about it. But you can. If you did, it would look like, I think I gave you the answer, didn't I?
Yeah.
If you did distribute it and solve for y, you would have y equals 11 root 3 over 5 times x minus 48 over 5. But at this point, I'll take either one. You got this far, I'm happy. So equations of tangent lines are messy in polar coordinates because you're taking things that are round and circular and trying to come up with straight lines, which is why it's such a mess. That's why the formula is ugly. Most of the time what we're interested in is the example that we did before this, where we were looking for horizontal and vertical tangents, because that tells you when the graph might, turn around, where you're going to have a horizontal or vertical tangent, and it gives you some of that information. But if you want the tangent line, say right here, you may have a line that's messy like that. Questions there? You think we're good? We didn't like it. I didn't ask if you liked it. I don't want to know the answer. I think I know the answer. I think I know the answer. Welcome back from spring break, right? Okay, before we move on to 10.4, I want to do one more thing, and let's talk about how to draw a rough sketch of something in polar coordinates without using your calculator. Not that you can't use your calculator, you can, but sometimes you just need to draw a rough sketch, especially with what we're doing in 10.4, to know what your shapes look like. So I'm going to show you how to do something like that. So this is not on your notes. I actually added it on the back of page, I think it's 102. You have a blank page for 102? Yeah, so I added this to 102. So imagine that you want to sketch r equals 3 sine theta. I want to get a graph of that. One way is to make a table. I think that's what we did last time, right? We made a long table and plotted points. Did you do that? It seems like so long ago. Earlier on an example, where would it be? I hope we did one of those. And we talked about it back in example 2 and 3. If you want to sketch the graph of that. Sketch the graph really means sketch it over here with x's and y's, right? But this is thetas and r's. So here's how I like to do it first. And I think the directions in our book, I wish I remember what they said. Let's see if I can find it on the lab. They say something interesting like, it says sketch the curve. You may find it helpful to first sketch the graph of r as a function of theta in Cartesian coordinates. So I'm going to show you what I mean by that. If this is theta and r, theta and r, kind of like if this was x and this was y. You know what the graph of the sine function looks like? Yeah, it starts here, goes up, comes down, keeps doing that, right? What does this particular one do? How high up does it go?
3.
It goes up to 3, down to negative 3. And how long until it gets back to where it starts? 2 pi, that's the period, right? So this is 2 pi, this is pi. This is a rough sketch of this function in what we call Cartesian coordinates. So that's like your x, y, it's your theta, and your r. What this does is it helps us to then change it into actual Cartesian with x's and y's. It's kind of weird. Remember that x equals r sine theta and y equals r cosine theta. We want to take that and kind of convert it into what the x and y's do. So when theta equals 0, where am I on this graph?
0.
0, right? So r equals 0. If r equals 0, what's x and y both going to be?
0.
0. So that gives me 1 point on the graph already. When theta equals 0, x and y are both going to be 0. So when I'm looking in the theta 0 direction, excuse me, remember 0 is this angle like where I start here, and we rotate around for our angles. If I'm looking in this direction, I'm going out 0. What happens when I'm at, what would that be, pi over 2? At pi over 2, my r is 3. Yeah, r is 3. So when I'm graphing it, pi over 2 is now looking straight up. That's pi over 2. I'm going to go out a distance of 3. So I started here and I end up there. I doubt I went there in a straight line. What happened to my r's as I went from here to here? R was 0 and r went up to 3. So my r's were increasing, right? Every time I went a little bit further away, the r got longer. So I started at 0. If I go a little bit of an angle here, I'm going to be a little further out. And if I change my, put these angles in. I'm just kind of estimating. If I now do another angle, I should be a little further out. And if I do another angle, I should be a little further out. And if I do another one, I'm even further out. I'm just kind of estimating, because this says every time I move a little bit of an angle, my r's are just a little bit bigger. So every time I look as I turn, I'm just reaching out a little bit further. So that's a quick way to sketch that part. And then as I move from pi over 2 to pi, what happens to my r's? They go right back down to 0. Exactly the same way they went up. So that helps me to do that part. Right? As I rotate here from pi over 2 to pi, my r's are getting shorter and shorter and shorter and shorter and back to 0 again. What happens when I get past pi? Like just a little bit of a fraction of an angle past pi. What happens to r? It's lower, but let's be more specific. It's negative. So if I'm at an angle a little bit past pi, like maybe this angle here, just a little bit past pi, if I'm looking in this direction, r is negative. So which way do I go? Backwards. I like pointing backwards. So instead of going this way, I'm going to go back this way and I'll be back over here. And then when I'm looking this way, it's still negative, just more negative. I end up, say, back over here. And every time I'm looking down here in this quadrant, all of my r's are negative, which just puts me right back to where I was. So I ended up, this was the first quadrant, that's the second quadrant, there's the third quadrant. I'm doing that again. And no surprise, guess what's going to happen for that last one? When you're looking down here, all of your r's are negative as well. So you end up right back where you started. Now, I can't show you how to see this. It's hard for me to show you what I'm looking at. All I can really do is try to explain it. My r's are increasing out to 3, and then they're decreasing back to 0. So, and this is as you rotate, right? Because as theta increases, as you rotate, your r's go out to 3, and then they come back to 0. So as you rotate from 0 to pi, you go out to 3 and back to 0. It kind of helps you graph a little bit of that. And as I go from here to here, my r's are all negative, so I end up doing that same circle twice. This actually, my picture's horrible, is supposed to be an equation of a circle. And I actually went around it twice by graphing from here to here. Sometimes that helps you to graph it. There's other ones that you can see better than others, but you want to think about, as I rotate, as theta changes, what's happening to r. We're going to see some of that as we go into 10.4. We're going to be graphing a lot of these because we're about to find areas in between these curves. Questions on that? You can always make a table. You can still use your calculator. Okay, let's move on to 10.4. Let's move on to 10.4. We'll get started on it, and then we'll take a break, and we'll spend some quality time there. So I am now flipping over to page 105. Introduce the formula for areas in polar coordinates. Areas and lengths. Arctic, remember that? It's been a while. So my first question for you is, what is the area of a sector? A sector being a piece of a circle. And you may not know that formula. But my question maybe before that would be, what's the area of a circle? If this was a circle, if I could draw, well, I can't draw, but pretend that's part of a circle. What's the area of that whole red circle? Are you laughing at my artistic abilities? I'm offended. Oh, no, not really. It's hard to offend me. Area of a circle is, somebody said it, pi r squared. So if this really were a circle, if I could draw, we agree that red circle would have an area of pi r squared. Well, this little, what we call a sector, is just a piece of that. A piece of that circle. What if it was, I don't know, 30 degrees? How much of the circle would that be if it was if this was 30 degrees? Yeah, it'd be like a percentage of 360. So if that was 30, we'd say 30 degrees out of 360 would be 1/12 of the circle. Right? If it was a 30 degree, it'd be 1/12 of the circle. So we do 1/12 of the area. We agree with that? If it was 45, we just figure out 45 is what fraction of the circle. So in general, the area of a sector is exactly that. We're going to figure out what fraction of the circle is it, but instead of degrees, we're going to do it in radians. So we would take our angle, whatever our angle is, and divide it by, what's the whole circle in radians? 2 pi. So this is just saying what fraction of the circle times the area of the circle. Like maybe my 1/12 times pi r squared. It's not always 1/12, but that's just for example. See that? A fraction of the circle times the area. What happens here? The pi's cancel out. And you get 1/2 theta. That's a really weird 1/2 theta. 1/2 times theta times r squared. Because the pi's are going to reduce. Okay? So here's my next question. What if I make this so skinny, that instead of theta, I'm not going to make it skinnier, it's just a small little change in theta. It's just a small change in theta, just the tiniest little angle that you can barely see. what would happen here? What'd you say?
Stick an integral sign in it.
I'm gonna end up with an integral sign, but if I just had one little tiny piece, and my angle was a small d theta, this would just become d theta right there, right? So I'm gonna call it an area of a sliver. I didn't make the sliver any smaller because you guys won't be able to see it. An area of a sliver is 1/2, of course I'm gonna put my d theta on the end because it looks prettier over there. That's the same formula. So the sliver is going to help us take the area of any shape in polar coordinates, which is your figure 2 and your figure 3 that you're looking at. So let me draw figure 2. So figure 2, here's polar coordinates. It just says, you know, here's some graph and we want to go from this angle here, which we're calling alpha, to this angle here. Oh, they're calling A and B, I take it back. I want to match our notes. Oh, no, they do. Oh, they're calling A and B. Angle A and angle B. They're not doing Greek letters here. That's your figure 2. And we want to know this area inside there. We want to know this area in here. Started at angle A, rotating until we get to angle B. It's clearly not a circle anymore, though, for sure. Agree that's not a circle? But if you take a small enough sliver of it, oh, look, lose my pen. One little tiny sliver in here. It's kind of close to a piece of a circle, right? It's got a little curve on there. If I make it narrow enough, it looks like a piece of a circle. Agreed?
Yeah.
So that one little red sliver right there has this area. So to find the total area in here, I'm going to take that one little sliver, but I want to start slicing my slivers way down here, right? Start over here, at there, and keep slicing it up all the way till I get to here. So that's where your integral comes in, right? So the area is the integral of all those little slivers added up from where to where? From whatever angle we start at to the angle we stop at, which in this picture was from A to B. This is how you find the area of anything that is in polar coordinates. I knew I was going to say that. So instead of adding up rectangles like you did back in Calc 1 when you had things in terms of x's and y's, we're now adding up little sectors, little tiny pieces of circles. So instead of slicing vertically, we're slicing as we rotate through the angles. So make sure you have that highlighted somewhere on that page. That's how you're going to find the area anytime you have an equation given to you in polar coordinates. Questions? It's weird, I know. No questions? Okay, so start with example 1. I'll do example 1, take a break. See if we can handle it. Example 1 says, determine the area of the inner loop of this equation here. So already we're going, what do you mean inner loop? So example 1, we want the area of the inner loop of this equation here, r equals 2 plus 4 cosine theta. What do they mean by an inner loop? What do you think we should do to figure out what they mean by that?
Is it the
Yeah,
inner
maybe graph
radius?
Go ahead.
The inner circle from
Mhm.
0 out to whatever its inner.
Yeah, it might be 0, it's hard to say. But basically, we want to graph it first so we can see what they're even talking about with an inner loop. Whether you graph it with your calculator or you graph it with a rough sketch like I just showed you with, like I did with that previous example, it's completely up to you. I am not an expert at graphing in polar coordinates, but I usually at least look real quick. Well, maybe I am an expert, I don't know. But I look real quick at some angles that I know. When theta equals 0, I can easily plug 0 in here and see what happens. If I plug 0 in here, I just need to know cosine of 0, which is 1. So that'd be 2 plus 4. So when I'm looking in this direction, I'm out here at 6. I know I'm starting there. By the time I get to pi over 2, now that's likely to start on the axis of the quickest. What's cosine of pi over 2? Gotta know your trick. 0. So that would be 2 plus 0. By the time I get there, I'm only out here now. What happens when I'm at pi? What's cosine of pi? Yeah, cosine of pi is negative 1, so that'd be 2 minus 4. So it's negative 2, so think about that. When I'm looking in this direction, that's pi, my r is negative 2, which means I need to do what? Go backwards. I actually end up here. Let me just pause for a moment. So I started here. Everything's rotating when you're doing polar. So I'm rotating from here to here. But now I need to figure out what the heck happened. How do I rotate from there to there? Like, how do I get there, right? I'm supposed to be rotating through there. When I'm in this quadrant here, between pi over 2 and pi, are my cosines positive or negative? You know? When you're between pi over 2 and pi?
Negative.
Negative, right? Because at pi over 2 it was 0, and then it gets the most negative by the time you get here. So everywhere in here I'm actually kind of going backwards. So what happens, I'm going to just finish sketching the graph and try to make it a little bit more accurate. It ends up doing something like this. I'm not an artist. It's actually what we call a limicon. But we talked about those last time. The cardioids look like hearts. The limicons actually have a circle in there. It kind of doubles back over itself. If you want to make a table, you could get a more precise graph. If you use your calculator, it'll do it fairly quickly. But you can see that it starts at 6. It hits up here at 2. It goes through 0, and then comes over here at negative 2 when you were in that pi direction, and then back around to where we started. So here's a rough sketch. So the directions say, find the area of the inner loop. It wants to know the area of this piece right here. Okay, great. Great. Area is this function, we just talked about that. So do I have R? Do I have R?
Yes.
Yeah, it was given to us. So I can set this up. The hardest part, everyone always tells me this, are the bounds. I could do 1/2 r squared d theta. 1/2 r squared d theta, I could plug that in, no problem. The hardest part of areas in polar coordinates is actually your trig to find the bounds. So I'm going to describe to you what happens as I draw this. So I start here at 6, I rotate here till I get to 2, then I come along, and what happened? What'd you say?
So when you just from 0 to 2, you're going to.
So you're kind of right, but we're talking about thetas. But right here, what's r right here? If I'm right there in the middle, what is my r value if I'm right there? 0, right? When I'm right there, r is 0. And then r goes out, and it goes back to 0 again. Right? So I started at r equals 0, I went all the way up here to 6, but from here to here, just to draw this loop, r went from 0 and back to 0 again. The r value. So all I really need to know is when is r equal to 0? When is r equal to 0? Because the inner loop starts and stops and stops where r equals 0. You got to be thinking in terms of radius, right? Not x's and y's. Do we agree with that statement? Okay, how do I find when r equals 0?
Is that
Set r equal to 0. 2 plus 4 cosine theta has to equal 0. R has to equal 0. Now we're going to use our fabulous algebra and trig skills. Bring that 2 over here. Divide by 4. Cosine of theta equals negative 1/2. 2 over 4, right? So here you need to know your trig. Chad's up here saying 2 pi over 3. What did you say back there, Joseph?
So can we do the arc cosine?
You could do an inverse cosine on your calculator. The problem is it's only going to give you one of the angles. So knowing your trig is going to make sure you can find both of them. So let's kind of talk through this. If the cosine is negative, which quadrant are you in? Second quadrant or third quadrant. I like to draw a little triangle. Like here's a triangle in the second quadrant where my cosine is negative because I've got a negative here and then my hypotenuse is positive. So I could be here with the relationship of, oops, this is not the right picture, negative 1/2. I also recognize the 1/2 tells me I'm dealing with one of these guys. Every time you got 1/2 or root 3s over 2, you're dealing with one of those. So I'm going to draw a little bit better picture. Here's one in the second quadrant where this is a negative 1 and this is a 2. This is negative x value and that's a 2. Where else could I draw it? In the third quadrant, right? Same thing, negative 1 and that's a 2. So it's connected. So you recognize this is a 30, 60, 90, hopefully. What angle is that? That told me 2 pi over 3. Theta equals 2 pi over 3. What's the other one? 4 pi over 3. Because if you think about pi over 3s, here's 1 pi over 3. Here's 2 pi over 3. 3 pi over 3. 4 pi over 3. Just count by pi over 3. So those are the two places that make this true, that make r equal to 0, which is the same as making cosine equal to negative 1/2. So we would need to go from 2 pi over 3 to 4 pi over 3. So to find that exact area, I have my equation, which is always 1/2 r squared d theta, but now I have the bounds. Starting at 2 pi over 3. Stopping at 4 pi over 3. We're going to calculate this after the break. You guys are falling asleep. But before we take our break, any questions on where this came from, and we'll finish it after the break. You've got to know your trig. All of chapter 10 is all this trig. And I always have students go, but Jill, I can't find the bounds. And that's because she doesn't know your trig. You don't know your trig. I can still hear the students from like 4 years ago. Jill, the bounds are hard. Yes, they are, unless you know your trig. Good? Ready for a break? Okay, let's take a good 10-minute break. We'll come back, we'll finish this one and do some other more skills next time. Got all these pictures of my husband like leaning over the edge of something. I'm like, no, step back up. They can tell me your camera. I'm like, no. Okay, so this is where we left off with, oh, the example doesn't have a number. It was example 1. Example 1? We set up the equation to find the area. So on the exam that's coming up in a couple weeks, there will be, just like we had last time, sometimes I'll just ask you to set up an equation to find an area. Sometimes I'll actually ask you to find the whole area. We're going to go through and find the whole thing this time. So this was the equation we set up. Questions on that? You think we're good? So how are we going to evaluate it? How do I evaluate this integral? Well, reminder of our brains used to be able to do this. Yeah, we'll pull out the 1/2. And what else? Yeah, multiply out this whole expression here. It needs to be squared. We can do that. That'll end up being 4 plus 16 cosine theta plus 16 cosine squared theta. d theta. Oops, I lost my bounds. So I multiplied it all out. Just using our algebra. And at this point, the 1/2 is out there, but see how these are all even? So I'm just gonna multiply it back through to get rid of half and even. Multiply my 1/2 back through. So it looks like. The integral from 2 pi over 3 to 4 pi over 3 of 2 plus 8 cosine theta plus 8 cosine squared theta. Now it's a review question. Can you integrate 2? Yeah. Can you integrate cosine theta? He says yeah. Speaking for all of you. What about cosine squared? Nope. What did we do with even powers of sines and cosines? Yeah, we had to use those little identities. He's trying to remember it.
I need to try to use 1/2 cosine.
Yeah, we had these two formulas, that cosine squared theta was 1/2 times 1 plus cosine of 2 theta. And sine squared theta was 1/2 times 1 minus cosine of 2 theta. Remember that from chapter 7? Never going away. So because we have a cosine squared, I'm going to replace it with this. Then we'll be able to integrate it. So I'm just rewriting that part. You're going to need lots of paper for this section. So the first two terms are no problem. We know how to integrate those. But the last one is going to be 8 times 1/2, 1 plus cosine of 2 theta. So I replaced my, another color. I replaced my cosine squared with that identity. See that? Now what should I do? Yeah, I can distribute that. This is 8 times 1/2, that's just 4. And I can distribute it through here. So we're just cleaning it up. We haven't done the calculus yet. We're still just doing the algebra. I'll recopy my bounds. So this is 2 plus 8 cosine theta plus 4 plus 4 cosine 2 theta. This is my 4 right here. And I distributed it through. Yeah, I'm going to simplify right now. Thanks for that suggestion. Combine my terms, I end up with 6 plus 8 cosine theta plus 4 cosine 2 theta. Yes. All of that was setting up the integral and simplifying the integral. Now we're ready to integrate. So, integral of this is, what's the integral of 6? Six theta, not 6x, right? D theta, so it's 6 theta. 6 theta plus the integral of 8 cosine theta. Integral of cosine is, that's the derivative. Integral is positive sign. So it's 8 sine theta. Here I have a 4. The integral of the cosine
2 sine 2.
is sine, when we're integrating, be careful. So it's going to be sine 2 theta divided by that 2. Right? Because when you're integrating, it's like what I call the mental U substitution, or the reverse chain rule. So the integral of this is sine of 2 theta divided by 2. And then we're going to still evaluate all that. from 2 pi over 3 to 4 pi over 3. Yes.
So, where do, you grade us on our work as well. So if for our work, because we already combined it to be 4 cosine 2 theta, couldn't we just be integrated do it as 2 sine 2 theta?
Oh, yes. Is that what
That's
you were
I said.
saying? Oh, okay, sorry.
Yeah.
Okay, sorry, I thought you were just talking about that part.
Oh, no.
So you're good, yes. A lot of it, if you're simplifying these little pieces as you go, I can follow it.
Okay.
I just don't like to simplify it as I go, because then someone's going, where did that come from? So he's saying that he would have already done this part in his head. I probably would have too if I wasn't doing it for you guys. So now we have to evaluate all that. I think I need a whole other board to evaluate it. Here we go. Now we have to plug in our bounds and ever so carefully evaluate. My notes here, so I don't have to look at the other side of the board. So we have 6 times 4 pi over 3. Right? 6 times 4 pi over 3. Plus 8 times sine of 4 pi over 3. Plus 2 times sine of what? I'm plugging 4 pi over 3 in right here. 8 pi over 3, because it's doubled. So this is plugging in all my 4 pi over 3s. Minus, now I have to do the same thing and plug in my 2 pi over 3. 6 times 2 pi over 3, plus 8 times the sine of 2 pi over 3, plus 2 times the sine of 4 pi over 3, because again it got doubled. I think I plugged it in correctly. Going from one board to the next, so you guys with me? You guys are all on the same page. Now we just got to start simplifying. This will reduce and just be 8 pi. Now we're at sine of 4 pi over 3. The quickest way for me to find it is to first find 4 pi over 3. And I like to do it this way. Here's 1 pi over 3, here's 2 pi over 3, here's 3 pi over 3, here's 4 pi over 3. 30, 60, 90. So this is negative because it's left. This is always positive. This is negative because it's down. This is my 4 pi over 3 in here. What's the sign of it? Close. You say root 3 over 2?
Yeah,
You're so close.
negative.
Negative, right? I think you get that. Negative root 3 over 2? Negative root 3 over 2. Plus 2 times the sine of 8 pi over 3. What the heck is 8 pi over 3?
2 pi over 3.
Yeah, it's the same as 2 pi over 3. Here's the way I like to look at it. Stop there. What's 6 pi over 3? 2 pi plus another 2 pi over 3, right? So 2 pi over 3 is this one up here. This one over here, where the sign is now positive. So 2 times positive root 3 over 2. What's that? Nothing? Trig. Trig everywhere. I need to get a trig shirt, don't I? There's no crying in trig. I think I need a trig shirt. You're right.
There's a cool website that sells shirts like that.
Yeah, I need to find it. I don't have any trig shirts, and the trig's really the hardest part of this. Okay, so this is 4 pi. We just did the sine of 2 pi over 3 a minute ago. What's that? Sine of 2 pi over 3?
Root or negative.
That's the positive one, right? Root 3 over 2 and 2 times the sine of 4 pi over 3, which was the negative root 3 over 2. Put that multiplication in here, make sure you see that. Messy. Gotta love your trig. Did I not warn you at the beginning of the semester? I think I did. Okay, let's see what we got. 8 pi. This is minus 4 root 3 plus positive times. Plus positive root 3 minus 4 pi plus 4 root 3 minus root 3. Simplifying here and here. I'm going to distribute that negative sign and we should be good to combine like terms. Minus 4 pi minus 4 root 3 plus root 3. I distribute this negative sign through there. So finally we get 4 pi. That's, let's see, there's minus 8 plus 2, minus 6 root 3. Had it in my head. Ooh, that's what I have in my notes. Must be right. Notice there are about 372 places to make mistakes. Those of you who are not neat and or organized, this is your chance to try to up your game. Because that's what you're going to need to do. Because you're going to lose one little negative sign in here somewhere and you're going to get so frustrated that you're getting the wrong answer. Can somebody tell me what this is as a decimal? 4 times pi minus 6 root 3. I want to show you what we actually just found. I always will want the exact answer, but I want to tell you what we just found.
2.174.
2.17-ish?
Yeah.
Yeah. If you remember, years ago, we were trying to find the area of this little loop. The area of this piece right here. It stretches out to 2, and here it goes like almost between 1 and negative 1. It's not perfectly round. So it's, if it were square, this distance is 2, that distance is 2. The area of that square is 2 times 2, it's about 4 for the area of that square. This is about half that area of the square, or rectangle, which makes sense, a little bit more than half. 2.17, we were finding the area of that. I like to always kind of change it into a decimal when I'm working with it to see if it makes sense. Like if it had come out negative, I know something would be wrong because area can't be negative. Or if the area turned out to be 48, there's no way the area of this little piece is 48. So I like to kind of just have a little ballpark to eyeball what it might be. That was long and exhausting. Let's talk about the pieces of that before we go on, because it's going to happen with all of them. So the first thing was, we had to find where the heck is this inner loop they're talking about. What is the inner loop? So you want to graph it first to see what you're looking at, to find your inner loop. That was our step 1. Step 2 was trying to figure out, okay, how do I actually get just the inner loop? Now, if you're not 100% sure how to do it, quite often it's where it starts at 0 and ends back at 0. We'll see a couple of those. But let's say you solved it. I don't have it here anymore. We got the 2 pi over 3 and the 4 pi over 3, and you're not sure if those are right or not. You can actually ask your calculator to graph this function starting at this and stopping here and see if it just graphs that inner loop. That'll kind of verify that you had the right bounds. If it gives you something else, then you know you've got the wrong bounds. But if you did this as your theta min and your theta max and ask your calculator to draw it, it would just draw that little piece. So you want to make sure you've got the right bounds. And usually you're going to have to solve using trig to get those bounds. Then you set up the integral, 1/2 r squared d theta, with the correct bounds. Then you have to carefully simplify, use trig identities, continue simplifying, so that you get to something you can actually integrate. Integrate, then very carefully plug in all your bounds, And then evaluate all that trig and simplify and not lose any signs or numbers or anything along the way. Questions? Wasn't that fun? So much fun we should do another one. Yeah? Let's do another one. Let's look at example 2. Let's look at example 2. Can I erase this? We got around down? Yeah? So example 2 wants the area in one loop of r equals 4 cosine 3 theta in one loop. So this one asked about an inner loop. This one asked about one loop. What should we do? Let's draw it. Okay. We could draw it on a calculator. I like to just start at 0 and see what happens when I start at 0. If I plug 0 into here, cosine of 3 times 0. So cosine of 0 is 1. 4 times 1. So if I'm looking at the 0 angle, I'm out here at 4. I got that much. Then what? I plug 0 into here for theta, because remember 0 angle is this angle right here. So you plug 0 into here, cosine of 0 is 1. 1 times 4 is 4. So when I'm looking in this direction, I'm going at 4. Then what? I'm okay with using your calculator too. I just want to know what you're looking at, how you're going to decide what it looks like.
Can we do pi over 2?
Yeah, we can try pi over 2. So in a sense, I'm making a little small table to just kind of graph it real quick. So at 0, we had 4. At pi over 2, it's going to be cosine of 3 pi over 2,
0.
which again is 0, times 4, so that's 0. So when I'm up at pi over 2, I'm here. That helps. What happens in between there, though? I think there's something else going on in there. Yeah, maybe pi over 4. Pi over 4 is not my favorite because the cosine of that's going to end up being, you know, it's going to have root 2's and whatever. We could do it to get a picture. So we could do a long graph, a long table to get the graph. But the whole point is just to kind of try to get a rough sketch of what it looks like and then figure out some bounds and so forth. I didn't hear you say.
2 pi over.
2 pi over 3 would probably be a good one. Anybody already graphed it on their calculator? What's it look like?
Looks like a fish kind of.
3 weeks.
Like a
Like a fish kind of.
like a fish. Where are its? So it starts here and does
Like a
this.
loop,
It goes
and then it goes
third
down.
quadrant.
Does it go down here like this?
Yeah, yeah,
They're supposed to be all the same size though. I'm not a very good artist.
like that.
It looks like that, but they're all the same size. Let me fix them. It does this, and then this, and then that. That's a little bit better. Maybe this actually connects it. Something like that. It's fine to use your calculator. Otherwise, you're going to spend quite a bit of time getting there, but you can. How do we do that? Is that what you say? Type it into your calculator in polar mode, and just tell it to go 0 to pi, 0 to 2 pi, whatever you want. Remember we talked about polar mode last time? If not, you need to make a table and plot it all out. So it wants one loop. Technically, my picture's horrible. Technically, all the loops are the same size. So whether we find the area in this loop, or this loop, or this loop, I don't really care. Just need to find the area in one of them. Describe to me how you're going to draw just one of those loops. If you want to draw just one of them, what happens? What'd you say, Joseph?
So it comes out almost like a circle, so it's either a circle.
It comes out from where though?
0.
Ah, it comes out from 0. So like, let's say I'm talking about this loop right here. To draw this loop, I'm starting at 0, and I'm going out to, must be 4, and then back to 0 again. Right, I started at 0, went out, and back to 0. So again, similar to that inner loop problem we just did, to draw one loop, you're starting at r equals 0, you're going out, and you're going back to where r equals 0. I need to know what angles give me that starting point and that stopping point. So it's actually almost the same, I think I've erased it now, that the loop starts and stops at r equals 0. So how am I going to find where r equals 0? Set it equal to 0, right? I want to know, when is this true? Oops, cosine 3 theta. If r has to equal 0, then cosine of 3 theta has to equal 0. When is the cosine equal to 0? Just the cosine, forget this 3 theta. At what angles is the cosine equal to 0? Pi over 2 is one of them. So 3 theta could be pi over 2. That's one place where the cosine equals 0. Where else?
3 pi over 2.
3 pi over 2. Where else is the cosine equal to 0? I want a few of them. Negative pi over 2. Negative 3 pi. Positive 5 pi. We could keep going. Every odd multiple of pi over 2 is where the cosine equals 0. 1, 3, 5, 7. There's an infinite number. They keep going before this and after this, right? There's a lot of them. How do I know which ones I want?
Feel like it'll work as long as you pick two that are sequential?
Exactly, I love it. Mike says, doesn't really matter, just pick any two that are sequential. So maybe you're gonna pick these two. From negative pi over 2 to pi over 2. From here to there. Guess which loop I'm gonna get if I rotate from here to there? The first one, right? The first one. We actually got part of it from going from 0 to pi over 2 already. We got half the top half of it. So you could do from here to here, that will give you this loop. If you went from here to here, from pi over 2 to 3 pi over 2, you actually end up with this one down here, because all of your r's are negative here. It doesn't seem right, but you're actually at this one second. And then do the other ones, you get this one, and then they just start repeating. So that's a really good point. As long as you pick two that are sequential, you're going to be fine. Again, I recommend putting it into your calculator. Ask your calculator to graph this, starting here and stopping here, say, to make sure you get just one loop. And it will just, if you do negative pi over 2 to pi over 2, it'll graph just that one loop. Oh, you were checking that, so I'm waiting for you to check that. Any of them will work. You get the same answer, it's pretty amazing. Okay, how do I set up the integral then? To find the area of, say, this loop right here, this red one. This red one.
Use the integral of,
The integral from negative pi over 2 to pi over 2, because we've determined that gives us that loop.
And then 1/2 times the equation.
1/2 times my equation for cosine 3 theta squared. D theta? Now we could evaluate from here, but I'm going to tell you that symmetry is your friend. Symmetry is talking about when half of the loop and the other half of the loop are the same size. Do you agree that this top half, if I could draw better, this top half of that loop is the same as the bottom half? If I could actually draw? What angle gives me the top half only? What angle? Starting where and stopping where? What angle is this to get to the end point? Instead of
Zero.
from- Yeah, starting at 0, right? Instead of going from negative pi over 2 to pi over 2,
And then you just
let's
have to
cut it in
do-
half and start at 0.
And then wouldn't you have to do the 1/2?
Yeah, so that, it takes care of two things actually. Let me write it down first and then talk about what it takes care of. Or, we're gonna take 2 times this. You don't have to use symmetry, but it's gonna make your life so much easier. 2 ways it does it, and I'm gonna write it down first. So this is what we just talked about. We could say negative pi over 2 to pi over 2, or we could just do half of it from 0 to pi over 2 and then double it. Half a loop and double it. 2 things that does for us. One is it takes care of this 2 times 1/2, the fractions go away. The other thing it does is you're evaluating trig at 0, which is one of the easiest places to evaluate trig functions. It's better than evaluating, let's say, pi over 6s and pi over 3s and whatever. So if you can use symmetry and start at 0, you want to. You understand what I mean now? You're going to get the same answer. So I'm actually going to do it this way, because these are going to reduce, right? Gone. So that's the integral from 0 to pi over 2. When I square that, I have 16 cosine squared 3 theta. Squaring the 4, squaring the cosine. And what do I have to do again? Got to use that identity again because of the cosine squared. (16 times 1/2 times 1 plus cosine of
6 theta.
6 theta, because I'm doubling this theta. This is a 3 theta, so we double it at 6 theta. So now what?
You can simplify.
Yeah, simplify. The 16 times the 1/2 is just an 8, so I can pull it all the way out front. So that's an 8 times the integral from 0 to pi over 2 of 1 plus cosine of 6 theta d theta. Integral of 1 is theta. Integral of cosine 6 theta?
1/6 sine 6 theta.
Beautiful. 1/6 sine of 6 theta. That's that reverse chain rule or mental U substitution. Evaluated from 0 to pi over 2. Zeros are always nice to plug in. Now I'm plugging those in. 8 times pi over 2 plus 1/6 sine of, I have to take 6 times pi over 2. So that's 3 pi. Minus 8 times 0 plus 1/6 sine of 0. Do not automatically skip this part, because if it was cosine of 0, it wouldn't be 0. It would have some value here. A lot of people don't plug in the zeros. You want to at least double check to make sure they don't have some value here. In this case, they're all 0, because sine of 0 is 0. So this part's all gone. It's not always the case, though. What's the sine of 3 pi? It's 0. Sine of all the multiples of pi is equal to 0. Sine of pi, 2 pi, 3 pi, it's all equal to 0. So that's 0. So my answer is 4, 5. 8 times pi over 2 is all I have left. Head's about to explode. This is as bad as it gets. I'm telling you, it's as bad as it gets. Okay, maybe the next example, but this section is as bad as it gets. You still good? Yeah? Okay, last example. We'll do arc length next time, I think. The last example talks about the area that's inside one curve and outside another curve. I need to make sure I draw them in 2 different colors so you can set it. We're just going to set this one up for today, and we'll finish it later. Where do you go? Inside, this is example 3. R equals 3 plus 2 sine theta. And outside, R equals 2. So we want to find the area inside the one curve, outside the other one. I'm going to draw a picture of it here, nice and big. Which of these curves do you recognize? Hopefully one of them. One of those should be one that you recognize without. R equals 2. That just means radius equals 2. Theta can be anything, so what is that? Just a circle, a radius 2. Okay, I'm going to draw that one in red. We'll attempt to draw a circle. Lily's going to laugh at me. That's pretty good, I have to say. It's pretty good for a circle. So there's R equals 2. The other one's not a circle. It's either a limicon or a cardioid. What's it look like? I don't have a picture of it on my notes. Really? You don't. Oh, I know which one this is. I'll tell you what I think it looks like afterwards. So again, I just like to put in a few values to see what happens. If I put 0 in here, it starts at 3. Actually, 3 plus 0. By the time I get to pi over 2, what's the sign of pi over 2? Sine of pi over 2?
0. Or 1.
It's 1. And 2 times 1, 2 plus, so it'll be all the way up at 5. 1, 2, 3, 4, 5. By the time I get to pi over 2, I'm going to be all the way up here. By the time I get back over here to pi, I'm back at 2 again. So this part actually does this. It looks the same. But what happens underneath there? It has a little bump. Yeah, it makes the cardioid. When you get to, what would that be? 3 pi over 2? What's the sign of 3 pi over 2? It's -1. So you'd have 3 minus 2. So you only go out as far as 1, which is right here. So what happens is when you get down on this quadrant, you've got some negatives. It actually does something like this. That's the little bump he's talking about.
Like a messed up heart.
A messed up heart, which is why we call them cardioids. So this was the green one, and this was the red one. And we want the area inside the green one, but outside the red one. Inside the green one, but outside the red one.
Oh, no.
Inside the green, but outside the red. Something like this area. with the picture. I have to tell you what I think that picture looks like. Every time I draw, this is what I see. It looks something like this. That's what I see when I look at it. Ever play Super Mario? You know Toad? It looks just like Toad to me. I can't draw, but it looks like Toad. I see his little, you know, he's got the big dots on his helmet. It looks like Toad, Super Mario. I played way too much Mario Kart in my life. You don't see it?
No.
That's what I see. He sees it. See, all the
I see like a mushroom from the bottom because the stem, because like the line going to the bottom, but I don't see anything else.
Yeah, if I hadn't put the green lines, I didn't draw like that. It looks like Toad. Super Mario, whatever it looks like, doesn't really matter. Okay, so we want the area inside the green, outside the red. I can draw a pretty picture of it. What do I need to find to get this area?
You need to put the area inside.
I need to find the intersection, he says. And what do you say?
Oh, so you need to put the area to intersection in there.
Yeah, because we need to know, like, remember when you're talking about polar coordinates, I'm going to put these together, everything's about rotating. We need to know when I'm actually going to get this curve. So like, let's say I start at 0. I'm rotating here and here, and I keep rotating. But right when I get to here is when that stops, that little piece of area stops. And technically, if I had started, say, over here, if I started right there and rotated around to here, at these angles, then I always would have the green one on the outside and the red one on the inside. There's nothing happening down here that I want in this little region here. So I need to find the points of intersection. I need to know where does this start and where does it stop.
Maybe something to equal each other.
So I'm going to set them equal to each other.
You have to see that 2 is equal to that.
2 is equal to that mess. So 3 plus 2 sine theta has to equal 2. And the question is, at what angles does that happen? This is why when you had pre-calc, they made you practice solving all those trig equations. So 2 sine theta equals -1. That's subtracting the 3 from both sides. Sine theta equals -1/2. So Chad tells me it's at 7 pi over 6 and 11 pi over 6. I'm going to draw you a picture to show you where he got that. If the sign is negative, which quadrant are you in? No, not 2.
3, 4.
3 and 4. If the sign is negative, your y values are negative. So you're down here. And if the sign is -1/2, that means that -1, 2, root 3, or over here, -1, 2, root 3, be negative. Those are my 2 options that would give me a negative sign. What angle is this little guy in here? 30. And if you think of it as a pi over 6, if I go all the way to pi, that's 6 pi over 6, plus 1 more, 7 pi over 6. This one is just a pi over 6 short of 2 pi. So this is 12 pi over 6, and you back 1 up, you're at 11 pi over 6. So that's where he's getting us. Or negative pi over 6, which we want to talk about because it makes a huge difference. So we could talk about it going negative pi over 6, or we could go around this way and make it positive 11 pi over 6. And in this case, it matters which ones we use to set it up. Let's start with the ones you gave me though, Chad. Let's talk about those. If we start here and stop at 11 pi over 6, from here to here, where am I in this picture? Say again, Chad, couldn't hear.
On the inside of that circle.
Yeah, so if you start at 7 pi over 6, you're here, and you're going to rotate till here. If I go from this one to this one, I'm not getting any of that area that I want. I'm getting everything except the area that I want. But if I start here and rotate around to there, then I'll get everything that I need. And so if I start here, you always start with the lower theta value. So I actually want to start with that negative. I want to go from negative pi over 6 to positive 7 pi over 6. So this is one where you can't just take any two that are in order, because you might get the one part that you want or the one that you don't want, depending. But if I start at the negative, rotate around to the positive, that'll give me the whole thing. What'd you say?
I don't have to do two integrals and add them together.
No, we don't need to do two integrals. We're
Yeah.
good.
But wouldn't that work though?
What'd you say, Joseph?
Could that work though?
Could what work?
Do the two integrals and have them together.
Well, I don't know which two integrals you're talking about, so
Well,
that's,
it'd be the same integral, it's just you'd have different bounds, it'd just be from 1 pi over 6 to 2 pi, but that's just a waste of time.
oh, so take one and subtract it from the other one, is that what you're
Yeah.
saying? Yeah, you
Yeah,
could, but,
add the two.
yeah, you could do two. I'm gonna use symmetry in a second.
Yeah.
But what do you do when you're talking about inside, I have two curves here? And remember our formula was, did I erase it already? I did. Our formula is the area A to B 1/2 r squared d theta. Bless you.
Thank you.
What do you think I'm gonna do when I've got two curves? I got two curves here.
Could you do the 3 plus 2 sine theta minus 2?
You're close. So not just subtracting the functions, but you're right in that I want the area inside this function, which would be all of it, including this part, right? The green one is that one. And then I want to cut that part out, so it'd be subtracting the area on the outer one. So essentially you end up with the area, I'll put the 1/2 out front, of the one function minus the other function, right? The outside function minus the inside function. So you could set them up as two integrals, but put them all together, it's easier. Okay. Everyone understand why it's a subtraction problem? One area minus the other area, but we can put them all together. So 1/2, what are my bounds?
Negative pi over 6 and 7 pi over 6.
Negative pi over 6 to 7 pi over 6. And then I need to put the outside function first, which is the 3 plus 2 sine theta squared minus 2 squared. My outer r squared minus my inner r squared. We're gonna finish this problem next time, but my question for you is, how can I use symmetry to make it look a little bit nicer and to be easier to evaluate?
Negative pi over 6 is pi over 2.
Negative pi over 6 to pi over 2, he says. Because if I start at negative pi over 6, and I go to pi over 2, that's exactly half, and then I can double it. It's almost always easier to double and stop at a pi over 6, or excuse me, a pi over 2, or a pi, or a 0, 3 plus 2 sine theta. It's 4, I squared that already. So multiply by 2, change it to only do half of it, and then we can keep going from there. Why is that preferable? 2 reasons. Why do I want to do this? It can't be because Jill said so.
You take the integral of sine, it's going to be cosine, and pi over 2, it's going to be 0.
Beautiful. So one thing is when we take the integral of sine, it's going to give us cosines. And cosines of pi over 2 are all zeros. You want to plug these into cosines? None of them are zeros. So we always want to use pi's and pi over 2's and zeros because it's going to make your sines and cosines be zeros or ones, which is a lot easier to work with. The other reason is it takes care of this fraction on here as well. Takes care of that. Which the fraction isn't as big of a deal, but it's going to make evaluating this much easier. So when I see you on Thursday, we're going to finish this problem. We're gonna talk a little bit about arc length and polar coordinates, and then we'll start getting into chapter 11. Everybody's head completely exploded? I'm gonna go to the lab right now, I'll be there for the next hour and a half.